I guess Raymond doesn't need too much of an introduction, but the one thing that I wanted to say, as both the president of the OpenAirInterface Software Alliance and the foundation, and also as a professor at Eurocom, he has his thoughts on ISAC, and yes, he will tell us about the ISAC support in OAI.
Okay, just a small disclaimer. I learned I was giving this talk on the weekend, so I didn't look at the program and I figured that out. So I'll talk a little bit about what I can actually call extra ISAC support, because there is already ISAC support. There were demos here, especially by I'll Be Smart and others. So it means different things to different people. If we look at ISAC from a GNB perspective, and I think I took most of this from a white paper from Ericsson. Basically, what we want to do is use the 3GPP RAN to detect various things or various features in the physical world. So the presence, like, is something there? Location, where is it positioned? The size and shape, what are its approximate physical dimensions? Its velocity, so is it moving and how fast is it moving? Its direction, where is it headed? I'll add another one that I don't always see. That's identification. What IMSI are we seeing in these measurements? That one has a lot of ramifications that I won't go into here, but that could be another one. So I asked my favorite AI tool to generate one type of UE perspective of ISAC, and I asked it to look at a UE that was detecting a blockage in the environment in such a way that it can inform the GNB that KPIs are going to degrade. Okay, so this is like a big picture of the thing, and you have to think of a UE here that has some sensing capabilities. It's not necessarily sensing the radio spectrum using 3GPP methods. It might also have an onboard camera, which some of my friends here studied at length over the last 3 years here in Porto. It might have a radar on the phone. But it'll almost certainly have some form of inference engine in it to be able to make local processing of whatever measurements it gets. Now, where 3GPP comes into the picture is the signaling needed to transfer that to the network. You might see some people suggesting we do over-the-top signaling, and inside of 3GPP, you might have methods that are going to use lower layers for latency reasons, so that the GNB or the edge next to the GNB could react more quickly. But this is one concrete type of scenario that we could think of from the UE's perspective. And most of what I'll talk about at the end is really the UE's perspective. We saw in the previous presentation there is a need for the UE in the experiments, even connecting to something like Ukuru. But now if we go to the GNB side, the other thing that would be interesting too, and several of the projects that we're involved in here look at actually the fusion of non-3GPP and 3GPP mechanisms on the GPP side, on the GNB side. So here's one example, and these are a couple of students from Eurocom about a year and a half ago that wanted to look at very, very cheap millimeter wave radar. So this was a 70 gigahertz millimeter wave radar. It's chirp-based, a very simple technology. But I don't know if this is actually going to work here. But you can get an idea of what you're able to do with a very simple, it's a system from TI. You're able to very quickly identify two objects that are moving around. You'll see that the two squares appear at one point in clusters. This is a $100 piece of electronics, but it's millimeter wave at 70 gigahertz. We're thinking about very complicated mechanisms that you integrate into a radio unit that's worth $30,000, where you can do it with a $100 add-on to a 3GPP network. The key thing here would be to synchronize this millimeter wave radar with the GNB, and then you could do things. You get signals from the GNB, you get identification from the radar, you put them together in a fusion center next to the base station. Those methods are okay too, and I would still call those ISAC, because you have signaling that's going on the 3GPP network. And from a commercial perspective, maybe it's better to do it with a radar like that than actually implementing radar inside of a GNB. Okay? But in general, we'd be looking at joint processing at the edge, where you have with devices that are co-located with the 3GPP RAN. 3GPP RAN would give information from the SRS, from the PRS, potentially in FR1 or even in FR2. And a lot of these kind of things were studied here in Porto in the Converge project. I think some of you might have gone to the Converge chamber, which was just on top of the demo room. That's a picture of it there, if you went to the chamber. So this was something where we were looking at the fusion of SRS and real-time camera measurements. So not necessarily a millimeter wave radar, but actual cameras. In the project, it was RGB, but it could also be infrared cameras for privacy reasons. And even looking at things like controllable risk reflections to aid in the vision, if you want, that you're getting from the radio network. So add reflections are somewhat artificially by using RIS. So these kind of things are also interesting from an ISAC perspective, that were considered in some of the projects here. So if we look at basically the extra ISAC support in OAI, what are we looking for in OAI and Duranta? Basically enhanced support for existing 3GPP physical channels that we don't have. And also some layer 2 and layer 3 support for ISAC within the current 5G framework. I mean, there are study items looking at where we have to go in 6G, but there's stuff in 5G already for doing ISAC. It's just not implemented today in OAI. Basically exploiting signaling on top of SRS, PRS. There's this NR-LPP protocol that is not necessarily completely implemented today. If you look at the Albi Smart demo, that they were doing ISAC based on feedback from the CSIRS. Okay, all of these things could be integrated properly. We heard about the need for DApps and the need for extracting IQ samples out of the radio. Today in OAI, we have T-Tracer support for doing that. It was in OAI even in 4G, but it needs to be enhanced. And so we also looked at this in the Converge project here for real-time IQ streaming. Also looking at O-RAN and AI-RAN extensions, so the recent work from Northeastern on the E3 support in OAI. And also looking for other integration of sensing technologies on top of 3GPP, O-RAN, and AI-RAN signaling. The other thing that I'll talk about now is this to support the development of a next-gen UE platform. I think in some of the demos that you saw here, the key element is the UE when it comes to doing ISAC type approaches. That was the central part in the Albi Smart demo. And essentially what we want to be able to do is provide a next-gen UE platform with 6G bandwidths and carrier frequencies. Okay? And also having AI-capable compute alongside the radio. This platform doesn't exist. You could build it from pieces. It would end up being a very expensive piece of Lego, but it doesn't exist off the shelf today. So I've summarized here basically what I just said. Inside the 3GPP mechanisms, what is happening now, there are enhancements in the SRS. So essentially there's one Francisco is finalizing here on aperiodic scheduling. Right? There's one pull request for that. That will be necessary. We also have to look at all the procedures necessary to do time difference of arrival on PRATCH, PUSCH, DMRS, and also on SRS. These are things that are partly in the implementation, but not completely in the implementation. With respect to the PRS, all of the layer 2, layer 3 procedures are essentially missing and have to be added. So all of this in the 3GPP space is stuff that exists. It's just a question of implementing it. There's no new research there. When it comes to non-3GPP, there is the pull request from last week from Northeastern on the E3 and DApps framework. There are enhancements for the T-Tracer that will be coming for real-time IQ streaming, in particular putting the SRS in there. That's not in the T-Tracer today. It's only the PUSCH DMRS. And this should, in my opinion, we should build this on top of what NI put in the code base last year. So they did enhancements on T and also have a complete data acquisition framework for both sides GNOB and UE, to be able to push the data into some form of a database or a metadata repository system. And this could lead to essentially providing data for AI training data models. And also whatever work is still going on XApps for control of sensing data. We heard that in some of the previous presentations. So this is work that's going on now. If I can just spend a couple of minutes on this, this activity that we're going to try and push within the community to work with some companies that can develop this. What we want to build as a platform is a deterministic radio engine with some AI-capable compute alongside the UE. Okay? So basically, you would have, in this, I hope this works. Oh, no, it doesn't work. You would have an RF front end, which should be 5G, 6G, potentially FR2, but initially FR1, which would have an RF interface, which is a typical one that you would find like a JESD 204C or D interface. Some of the high-end RF chips that can cater to 6G waveforms are using that. It should have TDD timing. It should allow for timestamping. It should allow for buffering and DMA at good speeds, and definitely should also onboard a GPS DO. Right, so that's what we look at in the RF subsystem. We're working with two solutions today, one of them from Texas Instruments, and there'll be another one that we aim to work with, which is developed closer to home by Sequence. These are all capable in this frequency range. There will be a small FPGA component here, which is necessary to buffer and stream data into the processing engines. So basically, what we want is to have this device which has the compute next to the RF. So we're not building a piece where we're taking a USRP and connecting to another compute. This should be a one box solution. And there are really two compute engines today that we're considering seriously. There will be one based on Jetson, but the high-end Jetsons. So that's a GPU-based compute with high-end ARM cores. And the other one, not too many people in the room know this, but we are actually also developing on Qualcomm Dragonwing right now. Right, so that is a second platform where the OAI code base will run for UE. It'll also run for GNOB, but that's not the purpose here. The key thing is that this compute has to be low power, and both of those are reasonably low power with good amount of compute. And then on top, of course, the OAI software stack. And this is meant to be interfaced with OAI, with Okudu, to be used in certain types of proof of concept demos in European and US projects, but also in the context, I hope, of ORAN, but definitely ARN Alliance type proof of concepts. So this is something that's coming. And I don't know if we'll show something already at the next OAI workshop, but it's coming. So basically the targets here is this is a mobile UE device. Okay, it should be about the size of this laptop screen or a tablet and have everything that I described there on it. So you can move it around. You should be able to use it for scenarios like I'll Be Smart showed, but you should also be able to mount this on drones, on aerial platforms. That should be doable. It should also be used as a fixed ground station UE. So if you want a roadside UE that is there, essentially implementing the vehicle detection that we saw, that would be another target for this. Before I conclude, the reason that we're looking at this is I believe that the community needs something that could be developed in a small series, like maybe 1,000 of these. So this is not something that we want to build like Lego. Okay, it should be an integrated platform. The integration is a necessary step here. That's it.